because log functions are inverses of exponential. So what are some other inverse functions you know? Addition goes with subtraction. They undo each other. Multiplication goes with division. Square root goes with squaring a number, x squared. So this is another set of inverse functions. And when we understand inverse functions, like when we try to solve an equation x plus 3 equals 7, what we're really doing is undoing the plus 3 by subtracting 3 from both sides, right? So to be able to solve a problem like 2 to the x equals 7.5, I need a way that I can undo the exponential function. I can't divide by 2 because this is an exponent. I can't take the square root of 2 because this is an exponent. So I need a way of undoing an exponent, and a log is going to be the answer to that. So first, this kind of takes you a step back to like algebra. Remember that a function is a relation in which each x has only one y value. So it has to be a function, right? The vertical line test checks that it's a function. So if a vertical line, crosses a graph twice, or I should say more than once, it is not a function. It fails the vertical line test. So if a vertical line crosses a graph more than once, it is not a function. So a graph that would pass the vertical line test might be a parabola, right? We know that that's a function. An example of a graph that would fail the vertical line test might be a parabola that's on its side. So the vertical line test, everywhere that you draw a vertical line, you can only touch the graph once for each of those instances. But here, if I draw a vertical line, I'm crossing the graph twice with the same vertical line. It's a relation in which each x has only one y value. So maybe you spent time in Algebra 2 talking about that, but most likely you didn't. They're really important now that you're going to see what an inverse function is, that we know what a function is. So an inverse function is the result of exchanging input and output values. So if you have a comma b, now you're going to have b comma a. So you just switch the x and y values and you go from inverse to original function. This is called function notation, and I hate this notation. So an inverse function is written f to the negative first. We just learned about negative exponents. A negative exponent usually means take the reciprocal. This does not mean to take the reciprocal. This just means inverse function in quotations. So I hate that they use that notation. To me, that makes it confusing. It makes you just want to take the reciprocal of the function, and that is not what it means. All it means is this is the inverse function, exchanging x and y. So an inverse, for example, would be like x plus 3 and x minus 3. Those are inverse functions. They're not reciprocals of each other. Domain and range flip-flop because x and y flip-flops. So domain of the inverse is the range of the original and vice versa. All right, so a one-to-one function. This is new. So each y value only has one x value for it to be a one-to-one function. It has to be a function first. So each x can only have one y, but now each y can only have one x. And the horizontal line test is going to test for a one-to-one function. So if a horizontal line crosses a function more than once, it is not 1-to-1. So notice I said it already has to be a function. So if a horizontal line crosses a function more than once, it's not one-to-one. So I'm going to bring our friend, I'm going to bring our friend the linear function right here, and I'll put a parabola over here. So this says an example of a graph that would pass the horizontal line test. It already had to be a function, right? So it already had to pass the vertical line test. Now it's passing the horizontal line test. So the function's one-to-one, and its inverse will be a function. And here it would fail the horizontal line test, right? It passes the vertical line test, but I just failed the horizontal line test. Its inverse will not be a function. This is the parabola x squared. What's the inverse of x squared? The square root of x. What does that graph look like? Half of a parabola. The reason is this part of the parabola is not pictured there, right? So because this does not pass the horizontal line test, I can't find its inverse. If I only look at this half of the graph, do you see how this is the inverse of it? So we're going to see why sometimes you have to restrict the domain of a function. So I'm not going to, test you on this vocabulary, but just when I use it, I just want you to know, like, oh, it wasn't one-to-one. I need to restrict the domain, things like that. From yesterday. So it says, here's the thing about inverse functions. They will always yield the following result when you compose them. If you plug f or g into f, everything will cancel and you'll get x. If you plug f into g, everything will cancel and you will get x. So I wanted to show using composition that these are not inverse functions, and show using compositions that these are inverse functions. So I'm going to try doing f of g of x. I'm going to take this stuff and I'm going to plug it into that first function for f. So this is why we talked about composition yesterday. So if I rewrite this problem, now I have 3 from the original problem, but instead of x, I'm replacing it with 7x plus 3. And then it says in the original function to subtract 7, so I'm subtracting 7. So now you simplify what you have. So I really have 21x plus 9, because 3 times 3 is 9, minus 7. 21x plus 2. So how did I just show that those are not inverse functions? This did not come out to x. If everything kind of magically goes away and cancels each other, it's an inverse. If you just end up with a function that's not x, it's not an inverse. So on the second one, if you do it f of g of x, or if you do g of f of x, both of them need to come out to x when you actually cancel everything. So if I'm going to take this g and plug it into f, I would write it as 1/2 2x minus 20, because that's going in for x right here, and then plus 10. So I just want you to show that all those things will cancel out and they just give you x. And then because this works, you also need to do it in the reverse order. Up here, the first one failed, so I had already proved it wasn't an inverse. Once it works in one direction, you need to plug the f into the g and prove it in this direction as well. Then it fails. I think it always is going to do it in both directions. I don't know if there's an example. I should find out. Will there ever be a time when it fails in one direction but not the other, right? I'm not sure. I don't know. It's not an inverse, but I'm not sure if it could work in one direction and not the other. Like if, I don't know. Will inverses ever work as f of g of x, but not g of f of x? I know someone who could answer that. Mr. Lund. All right. So we've got x minus 10 plus 10. See how that magically gave me x? So that's like, the first check. I'm plugging now this into this function. So now I'm going to start with a coefficient of 2. parentheses, 1/2 x plus 10, and then minus 20. So see how you get x plus 20 minus 20, right? So it works in both directions. So I'm showing that they're inverses by that rule of composition. A lot of algebra. So that's why it's nice to learn composition in algebra 2, because to learn about inverse functions, you need composition. We just never really did inverses. All right, so here's how you find an inverse. And I think this is what's on the homework. There's some log problems and some inverse problems on the homework. You can find them graphically and you can find them algebraically. What's nice is we already know the graph of an exponential function. I can find the graph of a log function graphically because they're inverses of each other. Same thing with algebraically. I already know my exponential equation, so I can find the log that's the inverse if I know how to do this. So this just says we know that a comma b on the original graph will become b comma a on the inverse. All you're doing is switching x and y. That's all an inverse does. So it says, let's graph the first function, 2x plus 5, and then graph its inverse on the same axis. So you should know how to graph this linear function, right? Start at 5, 1, 2, 3, 4, 5. My slope is up 2 over 1, so let's plot a couple points so that we can make a table and then switch x and y. So I have 4 points from this first function. And if I list those points, what would they be? So this is at 2 comma 9. I'm going to write it over here. 2 comma 9, 7, 1 comma 7, 0 comma 5, and negative 1 comma 3. What is the rule for an inverse? All it says I have to do is switch x with y, and I have found my inverse. I'm looking for another color pen. Here we go. So if I rewrite those points, I can graph 9 comma 2, 7 comma 1, 5 comma 0, and 3 comma negative 1, and this will produce my inverse. So 9 comma 2 is here, 7 1, 5 0, and 3 negative 1. This red line is the inverse function to the purple line. And I got it by switching my x's and my y's. And it says, draw in the line y equals x to show that the two functions are mirror images over the line y equals x. The line y equals x has a slope of 1, and it goes right through the origin. Right, so if this is the mirror, do you see how that's the reflection over the line y equals x? And it says, oh, it doesn't ask you to, but could I write the equation of that inverse? Can I figure out the y-intercept? See, down 1 over 2. What's the slope and what's the y-intercept of that red line? How could I write the equation? F inverse is equal to 1/2 x. See how it's up 1 over 2? See how this was a slope of up 2 over 1? And then where's its y-intercept? So if this, it doesn't go through an integer, does it? But I know the slope is a half, so it must be down at 1, 2.5, negative 2.5. Does that seem like if you composed it, right, you would end up with 2 times negative 2.5 plus 5 would end up canceling each other out? So we were able to find the equation from this graph because we know about the graph of a line. Can I go to the next one? All right, I'd like you to try the next one on your own, and then maybe we can do the cubic function together. So this is a linear function. So you're going to graph this line, record the coordinates, try to graph its inverse, and show that it's a reflection over the line y equals x. And I will help. So I should have started at -1, down 1, 2, 3, 4, and over 1. Up 1, 2, 3, 4, and over 1. There's that. What are my points? -1, 3, 0, -1, and 1, -5. So if 3 points is enough or 4 points is enough, so I'm going to flip them. So now I'll have 3, -1. Don't change the sign. If it's negative, keep it negative. All you're doing is just switching the position of x and y. Don't make them positive or negative. So 3, -1, -1, 0, and -1, 2, 3, 4, 5, comma 1. Is that what you got it to look like? So if I draw in my image or my mirror image of y equals x, it should be a reflection over that. So this is reflected over here and this is reflected over here. Did anyone try to get the equation? You can figure out the slope pretty easily, right? The slope is easy to figure out. The y-intercept on this one, can I figure out what the y-intercept is? Let's see, the slope is a fourth, so it must be at -1/4, right? So it would be a slope of -1/4 x minus 1/4. Because if I'm going from here to here, I'm going down 1/4. That must be at -1/4. Finding the equation's a little bit harder from the graph. That's why I'm going to show you the algebraic method, and then you can pick which one you like better. I personally would rather use the algebra than the graph, but did we get there okay? All right, so the last one I wanted to do graphically, and then I wanted to show you the algebra and have you do a couple practice, and then we're done. So graph number 2. This is the x cubed function from unit 1. So if I graph x cubed, let's remember those coordinates. 0 cubed is 0, 1 cubed is 1. What's 2 cubed? 8. 2 times 2 times 2 is 8. And what if I go in the negative direction? -1 cubed is -1, and -2 cubed is actually -8. So it's an S-shaped curve through the origin. And if I record those points, what did I just say? 0, 0, 1, 1, 2, 8. If I want to go backwards, -1, -1, -2, -8. If you have those points, you should be able to scramble them. So flip-flop x and y and graph the inverse. And you should recognize this inverse function. The inverse of a cube is one of our parent functions. So it'd be like -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. Oh, if you notice, these 3 points share the inverse points in common because what do they lie on? They lie directly on the mirror image line. If you lie on the mirror, you stay on the mirror, right? You can't reflect over the mirror if you're on the mirror line. So that's why those 3 points are shared. And then over 8 up 2 and over -8, oops, down 2. So this is like a sideways S curve through the origin, but I think you can see how the arms end up directly symmetrical. If I folded the paper in half along the pink line, it should line up. What's the function? What's that red function? What's the inverse of a cube? What's the inverse of a perfect square? How do you get rid of a square? Take the square root. So how do you get rid of a cube? You take the cube root. So this red function is the cube root of x graph. Negative 1/4 was the slope, and the y-intercept was tricky, but it is at negative 1/4. So it's negative 1/4 x minus 1/4. So what I said was it's hard to get that equation, so it's nice to have a fallback algebra method, or just walk around the building for a minute. This is a lot of algebra for one day. Okay, here's the other example. How can you do it without having to use a graph, especially if you're not as strong at graphing? Switch x and y in the equation and then solve for y equals. So to me, I like algebra. To me, this is a lot faster. In order to switch x and y, I just replace the f of x with y equals so that I can actually switch x and y in the equation. So then we're just going to literally switch this with x, and then 2y minus 3 divided by 4. So I literally switched x and y in the equation, just like I can switch x and y in the coordinates. And then the last step is to just get y by itself, right? A function has to be y equals. So what steps would I have to take to get this y by itself? First thing I would have to do is get rid of my denominator. So multiply both sides of the equation by 4 to get 4 out of the denominator. So now I have 4x equals 2y minus 3. So what would I do next? I want to get y by itself. So I need to add 3 to the other side. So 4x plus 3 equals 2y. And then the last step would be divide through by 2. So you could either leave your answer just like that, y equals 4x plus 3 divided by 2, or if you like to write it as 2x plus 3 halves, that's the same answer I just actually divided by 2. But your goal is to write it as y equals at the end. To me, that's a lot easier than graphing it, switching the points, guessing at the equation. This gets you the exact equation without having to guess. I go to the next page. So you are going to switch x and y and try to get the y by itself in these two functions. What? Sure. So can you try switching x and y and solving for y equals? So your first step is to rewrite it as x equals 3 times y plus 5 divided by 2. And now you have to do algebra to get y unstuck, get y by itself. Did you multiply by 2 to the other side, and then did you either distribute the 3 or did you divide by 3 first? You might have done two different paths, I'm not sure. So let's pretend you distributed the 3. So I multiplied the 2 to the other side and I distributed the 3. Subtract 15 and divide by 3, right? So I would have y equals 2x minus 15, and you could write it all over 3 if you wanted to. You could write 2/3 x minus 5 if you wanted to. If we hadn't distributed, it actually goes quicker, because then you have, let me show you this trick. If you have 3 halves right here, so I have 3 halves. If you have 3 halves, if you multiply by 2/3 on both sides, you've killed both of those with one step. See, now you have 2/3 x on the left equals y plus 5, so then you can just quickly subtract 5. So 2/3 x minus 5 or 2x minus 15 all over 3 is the inverse. The cubic one might be a little bit more challenging just because you haven't done inverses of cubes before. But you start by switching x and y. And then because the y minus 1 is stuck under the cube root, your first step is to cube both sides of the equation. So x cubed equals y minus 1. So once I get rid of the cube root, now I can just add 1 to the other side to finish the problem. So y equals x cubed plus 1. And we're not going to spend a lot of time on inverses, so you don't have to be super strong at finding the inverse, but we're going to do enough of them that we'll see it. Okay, so I think I'm going to